Well, it's my great pleasure to be able to introduce Professor Sarah Hurst, who's today's colloquium speaker, visiting us from Johns Hopkins. So I first met Sarah a few years back when we were undergraduates together at Caltech. Since then, she has, both through theory and laboratory experiments, really been pushing our understanding of the atmospheres and chemistry of places like Titan and other outer solar system bodies. So she did her PhD in University of Arizona, mostly on theory, figuring out things such as the origin of oxygen in Titan's atmosphere. After that, she made a very brave move of doing a postdoc focused almost completely on laboratory experiments. She brought her NSF fellowship with her to Colorado. And I think one of the experiments that got a lot of attention that she did was simulating the complex organic chemistry that you should find in Titan's atmosphere and showing how easy it is to form sort of prebiotically interesting molecules under those conditions. So after that NSF fellowship in Colorado, she joined the faculty at Johns Hopkins this past fall and is now setting up, or I think maybe already has set up, her own laboratory there. And I'm really excited to hear about your results on both laboratory and theory. So welcome and thank you.
Thank you so much. It's interesting having spent many years at different institutions, how similar a lot of the work that Karin and I are doing these days actually is. So I just wanted to say thank you. I've had such a wonderful time today. Fortunately or unfortunately, I'm not sure which, I've had so many amazing conversations with people. I fear I have not saved any brain cells for my talk. So we'll see how this goes. I'm going to tell you a few different stories about things that we've learned about haze formation in planetary atmospheres by doing laboratory simulations. But I want to motivate that work a little bit by telling you first why we've actually started doing these things in the lab when we have places that we can go in the solar system. So maybe not. Before I do anything else, though, I really need to acknowledge the group where I did my postdoc at the University of Colorado. All of the work that I'm going to talk about today was done in that group in the laboratory of Maggie Tolbert. And as Karin had mentioned, this work was all funded by my NSF Astronomy and Astrophysics postdoc fellowship. So if we're going to talk about haze formation, studying haze formation, the very best place in the solar system to look is Titan. And I'll talk about why that is in a minute, but I know that not everybody has the pleasure of studying Titan and thinking about Titan every day, so I want to just kind of get everybody up to speed a little bit. So Titan is really a unique body in our solar system. It's the largest moon of Saturn, and with a diameter of about 5,000 kilometers, it's actually the second largest moon in the solar system. It's bigger than the planet Mercury, so this is a substantial body. It has a mass of about 0.0225 Earth masses, so still smaller than Earth, but not doing too badly. And the density is about 1.9 grams per centimeter cubed, so this means that it's about half rock, half water ice. We know from measurements made by the Cassini spacecraft that Titan is at least partially differentiated, and so the crust is almost entirely water ice. Our surface temperature is 94 Kelvin, so it's quite cold. But the reason why I'm here, and the reason why Titan is so unique and important in our solar system, is that it's the only moon in our solar system that has a substantial atmosphere. And so that raises a lot of questions about formation and evolution mechanisms for all of the large moons in our solar system. So going forward, we need to know a little bit about the atmosphere. So Titan's atmosphere is actually quite dense. It's about 1.5 bar. It's mostly molecular nitrogen. So this is one of the other reasons why Titan is so unique and interesting in our solar system. It's the only other substantial molecular nitrogen atmosphere in our solar system besides our own. And so if we're interested in studying processes that may have occurred in the Earth's atmosphere prior to the origin of life on Earth, then this is the only other place where potentially a similar chemistry was occurring or is occurring. And so I always like to tell people, NASA's not going to fund a time machine. But we can fund missions to go to places that may be analogs of the processes that were occurring on the early Earth. Besides molecular nitrogen, the other main constituent in Titan's atmosphere is methane, at about ranging between about 2 and 5%, depending on where you are in the atmosphere. From that methane and nitrogen, photochemistry results in the formation of numerous complex hydrocarbons and nitriles. This chemistry is driven mostly by UV photons, about 90% driven by UV photons, but also input from the Saturnian magnetosphere of energetic particles drives this chemistry as well. One of the things that's really unique about Titan, though, and why I find Titan so interesting, and Karin alluded to this a minute ago, is that the other thing that makes Titan unique in our solar system is that we do have a fairly reducing atmosphere, mostly molecular nitrogen and methane, but there are some oxygen-bearing molecules in the atmosphere. 3 have been detected thus far: CO, CO2, and water. Of those 3, CO is the most abundant, with an abundance of about 50 parts per million. That doesn't sound like much, but that actually makes CO the 4th most abundant molecule in Titan's atmosphere. And so because of that, we have this very interesting situation in which we have a reducing atmosphere. Those types of atmospheres have been shown to be favorable conditions for forming organic molecules, but we also have the presence of oxygen. And so there's the possibility for doing some really interesting chemistry in terms of producing molecules made out of CH, N, and O. And we know that here on Earth, all of life on Earth is based on molecules made from those 4 atoms. One of the things that I didn't mention on the previous slide is that this photochemistry that I mentioned briefly actually produces this very complex haze. And so that's kind of what you're seeing, what this image highlights. You can see there's actually a couple of really amazing things on this image. We had a vortex form at Titan's South Pole a couple of years ago, so we've been watching that happen in real time. There was a paper that came out recently. People think that that is a giant cloud of hydrogen cyanide ice, which is kind of incredible. I always tell people Titan's a nice place to visit, but you definitely don't want to live there. You can also see the haze structure in the atmosphere. This is what we call the detached haze layer. It turns out that the location of the detached haze layer varies seasonally, and so there are some seasonal dynamical processes that are resulting in the formation of that particular structure. And then you can also see in this image our global haze layer, which is present all the time globally. It's quite thick. You can't actually see the surface. So, kind of a summary of all of those statements is that Titan's unique in our solar system because it is reducing, but it does contain oxygen-bearing molecules, and so this leads to the possibility of some really exciting chemistry that can be occurring. So how do we study Titan? Well, I think probably a lot of people in this room could come up with some ideas, but our first real glimpse of how interesting Titan might be in terms of organic chemistry came from the Voyager spacecraft, and came in 2 forms. The first form is this image, Titan as the orange ball. There was a April Fool's Day post yesterday of Cassini's most recent image of Titan, and it was a picture of an orange, which is a pretty decent approximation if you really think about it. Although maybe the organic chemistry on Titan is actually more interesting than the chemistry of an orange. I haven't really thought about it. So, of course, this kind of image is just torture for scientists, right? Because there could have been, Titanians standing on the surface waving at Voyager, and we would have had no idea because we couldn't see the surface at all with any of the instruments that Voyager carried. But we did get one glimpse of how interesting Titan is, and that came in the form of data from the infrared spectrograph carried by Voyager, IRIS. And so what you're seeing here is a spectrum, obviously, and the detection of numerous complex hydrocarbons and nitriles in Titan's atmosphere. And so, of course, now we have a planet where we cannot see the surface, but we know that the atmosphere is full of organic molecules, which is even more torture. So we wanted to go back, obviously, because that's what planetary scientists want to do. And it took quite a while, but we now have the Cassini-Huygens mission. So Cassini-Huygens is a joint NASA-ESA mission. It was launched in 1997. It arrived at Saturn in 2004. So we've now been in orbit around Saturn for 11 years. Still functional for at least a few more years. The current end of mission is September 2017, which is approaching much faster than I think any of us would like to think about. So this is the spacecraft while it was getting ready for launch. One thing that I always forget to point out to people in this image is that these are actual humans for scale in their little bunny suits. So Cassini is not a cute Mars rover. She is a school bus-sized spacecraft full of science. And the other thing that you'll see here is this, this gold circular thing is the heat shield of the Huygens Probe. So the Huygens Probe was dropped through Titan's atmosphere on January 14th, 2005, and did measurements all the way to the surface. So we have measurements that were done, that are done using remote sensing instruments on the orbiter. We have in situ measurements that were done by the probe, and Cassini also carries some instruments that do in situ measurements in the top of Titan's atmosphere, which I'll talk about more in a second. So we have quite a few ways to study Titan from the spacecraft. So this is our $4.5 billion fuzzy orange ball. so higher resolution than what we got from Voyager, but still an orange ball. I'm going to just walk you through for a minute some of the things that we've learned about Titan from Cassini to give you some context for the kinds of questions we're trying to answer. So luckily, we learned our lesson from Voyager, and so we weren't only carrying cameras that looked at visible wavelengths. So we've been able to characterize a lot of different parts of Titan's atmosphere and its surface, as you'll see in a minute. So we've learned a lot more about the haze. So this is just an image of the haze, and you can see that there's quite a bit of structure. We've been able to characterize some of that structure, and also, as I had mentioned, some of the seasonal behavior. So Saturn year is 30 Earth years, and having been there now for 11 years, we've actually been able to watch the seasons change and start to see how the atmosphere is changing with season. We think that the haze is mostly composed of some of those things I alluded to before, hydrocarbons and nitriles, aromatics, maybe some amines. If it's an organic chemistry word, it's probably there somewhere in some form. And one of the other things that's kind of interesting about Titan is that we have clouds on Titan. So not only do we have this thick global haze layer, but we also have methane storms. And there's some evidence of ethane clouds as well. And then, as I mentioned, we think this cloud that has formed in the south polar vortex is probably hydrogen cyanide ice. One of the reasons that we care about these environments is that the haze particles in Titan's atmosphere can act as cloud condensation nuclei to help form these clouds. And so that's one of the reasons that we're interested in the properties of the haze particles in terms of understanding the microphysics in the atmosphere. So now we can see what Titan's surface looks like, finally, after so many years. Using very narrow wavelength filters, we can see through some of the methane windows in the atmosphere down to the surface. And you'll see, and this is very important scientific description of Titan, that Titan has two kinds of environments on the surface. It has things that are bright and things that are dark. Okay? So if you learn anything from me today, there's two things on the surface, dark things and bright things. So what are these dark things and bright things? Well, luckily, we sent the Huygens Probe to the surface. And you have to forgive the poor, plucky Huygens Probe because this camera was built a long, long time ago. And so this is a very, very beautiful image that is not quite as pretty as some of the planetary images we get now, but it was the best it could do at the time. And so this is the image taken by the Huygens Probe from the surface. And as I think many of you would see, we seem to have landed in some kind of wash or stream bed. We see rounded cobbles, which I would just like to point out were discovered on Titan before they were found on Mars, FYI. However, as I mentioned before, Titan is differentiated, and so whatever silicate materials there were when Titan formed are almost all in the interior. So these pebbles, these cobbles, are not made out of rock in any sense that we think of for Earth. They're almost certainly either water ice or organics or some combination of the two. And so one of the kind of guiding principles of how we think about Titan is its familiar physics and weird chemistry. So that's a little bit about the surface. So the white things on the surface in general are bedrock, which appears to be water ice or some combination of water ice and organics. So what about the dark things? So Cassini also carries a radar, which doesn't care about the atmosphere at all, which is very useful for us for studying Titan. And Cassini has discovered large lakes and seas, mostly in the North Pole. And you can see that these look very Earth-like. There's rivers and streams. The lakes seem to follow the topography, so it looks as if they've filled in with liquid. The lakes are almost certainly mostly methane and ethane. Ethane is one of the primary products of the photochemistry occurring in Titan's atmosphere, and then it condenses out. So the lakes are one of the places that we think are most interesting for chemistry on Titan, because they can take the organic molecules that are produced in the atmosphere and then further process them once they go into the lakes. And so you have this liquid where things that are soluble will dissolve, things that are insoluble will fall onto the bottom of the lakes where they may be in contact with water ice. And so there's a lot of interesting possibilities for the kinds of chemistry that might be occurring. People are starting to think about what kind of membranes could you form by taking these organics that are made in the atmosphere and putting them in a liquid. And so there are some really interesting questions about what life might look like in the lakes on Titan. This is another reason why we're trying to study what the haze particles may be like. So, oh wait, I forgot. So, important thing. Okay, the light things are bedrock. The dark things, if they're at the North Pole, are lakes. And if they're anywhere else, they're dunes. So this whole thing, all of that dark stuff, it goes all the way around Mid-latitudes, they're all dunes, extensive dune fields. Again, as I mentioned, there's no silicate at the surface. So these dune fields are presumably sand-sized particles that are composed of organics, or potentially organics mixed with water ice. So again, this is one of the reasons why we're so interested in the haze. Titan, more than anywhere else in the solar system, and as far as we know, anywhere else in the universe thus far, has a very unique connection between its atmosphere and its surface. Most of the materials available on the surface to be transported by fluvial processes, to be transported by aeolian processes, or modified by chemistry, started out in the atmosphere first. And so if we want to understand anything about what's happening on the surface, we have to understand the chemistry that's happening in the atmosphere first. One other area that is potentially interesting on Titan for chemistry are impact craters. When you form an impact crater on Titan, you will form a reservoir of liquid water. The top freezes over very quickly, but then it acts as an insulating layer. And so a lot of modeling work has been done to show that you could have liquid water present on the surface for maybe 10,000 years. And then you would have organics that have never really met that much oxygen suddenly in contact with liquid water for a period of time. And even though it's quite cold, so reaction rates would be slow, there's been lab work that's been done to show that these organics will hydrolyze and that we could form amino acids, those kinds of things, in these pools of liquid water. So that's just kind of a little bit of an overview of the things that we've learned from Cassini and one of the reasons why we're so interested in studying the chemistry that's occurring in the atmosphere. So why do we care about haze? Well, I just talked about a lot of those kinds of issues, but there's, kind of practical concerns. The signals present in the remote sensing, so anybody who has to deal with dust, as in get it out of their way, would be annoyed by our haze particles in the atmosphere. We also have to think about the fact that it affects the radiation budget of an atmosphere and a surface. Because particles absorb and scatter light differently than gases do, having a haze layer could mean the difference between a habitable surface temperature and a surface temperature that is not habitable. And so this is something that we need to start thinking about, not just for Titan, but exoplanets. How does the haze layer affect the radiation balance? And this is also an issue that is important for the early Earth. Another reason that we're so concerned with the haze, which I think is really what I had emphasized on the previous slide, is that, at least for Titan especially, the haze is a source of organic material to the surface. And so if we want to understand the entire organic inventory of the body itself, we have to understand the haze particles. And finally, and this is one of the things that I'm most interested in, although it's probably the hardest one to sort out, is that on Titan at least, as I'll show in a second, the haze particle formation starts very high in the atmosphere. So if you were to go to Titan and scoop up some of this material on the surface, you would hold in your hands material that has experienced every single environment in Titan's atmosphere, every pressure, every temperature, every radiation environment, every chemical background, transport processes, and there should be a record of those things in these particles, but we have to figure out how to sort that information out. So you can envision doing things at some point like drilling a core of these organics on the surface and trying to plot a climate record of Titan by looking at what you found. Of these two are the ones that I care about the most, although the other ones are important too. So I put together a rather ambitious abstract, which we will not get all the way through. So a couple of things I'm going to talk about. One of the things that we're really interested in is understanding how energy source affects the haze particles, and I'll give you a little bit more background why that is in a second. Another thing that we're really interested in, which is quite practical, is actually what's the density of these particles in Titan's atmosphere, and I'll show you why when I get there. And then I think the last thing that I'll be able to cover is what is the effect of CO on forming aerosols in a planetary atmosphere. So how does energy source affect the formation? Why do I care about energy source? So one of the things that Cassini has really done for us is fundamentally altered our understanding of the complexity of the chemistry in Titan's atmosphere. So prior to the arrival of Cassini, the heaviest molecule that had ever been detected in Titan's atmosphere was benzene. So C6H6, it has a mass of 78. And so there's an instrument on Cassini called CAPS, the Cassini Plasma Spectrometer. It was designed to measure very small ions in the Saturnian magnetosphere, so things like oxygen and nitrogen, right? Very low mass. But you would think potentially, if you're flying through the top of Titan's atmosphere, which we do on occasion, that the data from CAPS might look something like this, right? If our heaviest molecule in the atmosphere is C6H6, then maybe we have a mass spec, so mass to charge on the y-axis, or x-axis, number on the y-axis, would go up to about 100, okay? So the actual CAPS data looks like this. That's a log scale, which is not a thing in mass spec for the most part. And I can tell you that the CAPS team, they are not atmospheres people, right? This is an instrument that was designed for to study the magnetosphere. And so they spent a lot of time internally discussing the data from the Titan flybys before they told anyone what they were seeing, because they thought they were going crazy. And they were afraid when they told the atmospheres people that they were going to get laughed at. It turns out, I think, they made the most amazing discovery of the entire mission, to be honest, but I'm a little biased. So it turns out that CAPS is detecting very heavy ions in Titan's ionosphere. This is high up. We're at an altitude of about 950 kilometers for this data. We're in the ionosphere. The mean free path in this region is something like a kilometer, okay? And we're seeing molecules with a mass to charge of about 10,000. So how you build a molecule that large when you're barely ever colliding with anything is an open question for us right now. And just for those of you who don't think about molecules very often, just to give you a sense of how wrong we were in our understanding of Titan's chemistry, that's what a benzene molecule looks like, right? C6H6. I spent one horrible day in ChemDraw trying to draw a molecule that had a mass of 10,000 AMU, which ChemDraw does not like. It crashed a lot. And that's what it looked like. But that's not a real chemistry thing. I just, stuck a bunch of things together. But just to give you a sense of scale of how far off we were. Of course, one of the things that's so incredibly frustrating about this, but it's motivated a lot of my work for the past few years, is that this instrument was not designed to do this. Okay? We have no mass resolution that can tell us anything about what these molecules are. So all we know is that they're there, but we have no prayer of identifying them from the data that we have. And then the other problem that we have is that we can't solve this problem with modeling, which is the other tool that we usually like to throw at this. This is actually how I got into doing lab experiments, because I started out doing photochemical modeling, and then they told us there were molecules that had a mass to charge of 10,000, and we're like, okay, we can't do a model. Photochemical models are really good up to about benzene for Titan's atmosphere, but, there's a situation there. So we had to move into the lab. But this discovery has really dramatically altered our understanding of aerosol formation in Titan's atmosphere. And so I'm going to show you why in a second. It's not just these heavy ions. From the UV instrument on the spacecraft, we actually see particle extinction all the way up to an altitude of about 1,500 kilometers. So there are particles up there, which is just crazy. I realize that it may not seem crazy to any of you, but it's still crazy to me. So why do we care that the haze is forming so high up? This is a little schematic of Titan's atmosphere, which is probably overly complicated for my purposes, but the temperature is on the x-axis. You can have altitude or pressure depending on your favorite units. And so the temperature profile is here. It looks very Earth-like. And what I really want you to see is that this is where Cassini can come down to. So the closest flybys we get are about 800 kilometers. Prior to Cassini's arrival, and these measurements by CAPS and the UV spectrometer, we thought that the haze formed where we see it, which is down here. Okay, the main haze layer is in the stratosphere. The detached haze layer, well, I have yet to make a plot where I can make that thing move. I think it's down here these days. But very, very deep in the atmosphere compared to where we're seeing these heavy ions. And so what I've done here is shown you a little bit about the energy available for chemistry. So FUV photons make it quite deep in the atmosphere. They'll make it almost to the surface. But our more energetic photons, Lyman alpha, UV, and then our energetic particles that are coming from the Saturnian magnetosphere do not make it that deep. And so prior to Cassini's arrival, we really thought that we were making haze with FUV photons, which are not energetic enough to dissociate N2. And so probably the haze would be composed mostly of hydrocarbons, right? Which is less interesting for life, because we really want that nitrogen in the molecules if we're going to start talking about prebiotic chemistry. But we now know that the chemistry is happening way up here, where not only do we have FUV photons, we have Lyman alpha photons, we have EUV photons, we have energetic particles, we can dissociate as much nitrogen as we want. And not only that, but something else that I neglected to mention is that Cassini has also discovered that there are O+ ions precipitating into Titan's upper atmosphere. It turns out that the source of these ions are the plumes of Enceladus. So what we have here are very heavy ions detected by CAPS, very high in the ionosphere, a whole bunch of energy running around, and oxygen precipitating into a reducing atmosphere. And so to me, this is a prime environment for forming things that might be interesting in terms of prebiotic chemistry. So the question is, how does this difference affect our understanding of haze formation and the possible haze composition? Because we have two very different energy environments. And it turns out that although people have used lots of different energy sources to make haze analogs in the lab, people have done it in different labs. And so it's very hard to compare, okay, well, these people did photons here, and then this other experiment used X-rays. And so it turns out that our experimental setup at the University of Colorado was particularly well suited to study the effect of energy without changing any other variable. So that's what we decided to do. So this is the experimental setup at the University of Colorado. This is a fairly typical haze simulation experiment. So we take our gases, we can mix them in whatever proportions we like. We flow them into a reaction cell where we can expose them to one of two energy sources. So all the experiments in this case were run at atmospheric pressure, but this was Boulder, Colorado, so it's 80% of sea level. It's about 630 torr. We run these experiments at room temperature. We can talk about that later. I know Titan is not room temperature, I promise. One of our energy sources that we use is a FUV source. So this is a deuterium lamp. It has a magnesium fluoride window. We get photons from about 115 to 400 nanometers. We have a peak at 121. We can use these UV photons to initiate the chemistry that leads to particle formation. We can also use, and people always say to me, people use these for science. We also use a Tesla coil to generate a plasma, which will initiate chemistry. And the thing that's nice about the Tesla coil is that the FUV photons are not, as I mentioned before, sufficiently energetic to directly dissociate N2. And so we need an energy source that can actually break that triple bond in nitrogen if we want to try to simulate the chemistry happening in Titan's ionosphere. So we can use one of these two energy sources. Once we do that, we analyze all of our products in real time, which is one of the things that makes this experiment very unique. We're the only people in the world that do it this way. So the products immediately flow out of the reaction cell and into one of, I don't know how many instruments I put on here. 3. We have 3 instruments this time. So one thing that we can do is we can measure the gas phase composition, so our gas phase products. And we do this using a technique called proton transfer mass spectrometry, or PITMS. Another technique that we can use is high-resolution time-of-flight aerosol mass spectrometry, or HRTOF AMS, but I will probably just call it AMS for everyone's sanity, although that probably means something different to at least some people in this room, which always confuses me. They put an aerosol mass spectrometer up there? That's amazing. No, wrong instrument. And that gives us the particle composition as a function of particle size. So we can measure both our gas phase products and our solid products, which is important for trying to understand how what the chemical processes are. And finally, one of the other things that we can do, which will be important not just for this study, but for the one I'll talk about afterwards, is we can use something called a scanning mobility particle sizer, which gives us the particle size and number density and can also tell us the total amount of stuff we're making. So how big are our particles? How many of them are there? And so one of the things that we found is that, first of all, our gas phase measurements show the heaviest products that have ever been detected from a Titan atmosphere simulation experiment. I suspect that this is only because of our analytical technique, not because we're somehow better at making heavy things than everyone else, but nonetheless it's kind of exciting. And so you can see that there's this very regular structure that's indicative of carbon and nitrogen, and looks pretty typical to a lot of other experiments. But one thing that you'll see, the top mass spec comes from our UV source, and the bottom actually comes from the Tesla coil, which I'll call Spark. So you can see that they're actually quite different. The Spark experiments produce heavier things, they produce more of them, and it turns out the composition is a little bit different, which I'll show in a second. So this is what I just said, that the gas phase products, there's more of them in the Spark experiments than in the UV experiments. This is just the total abundance of stuff we're producing as a function of methane in the initial gas mixture. So we did a wide variety of methane abundances. 2 reasons. One, just to kind of map out phase space so we can try to understand the processes better. But the other reason is that the abundance of methane in Titan's atmosphere has almost certainly varied over time, because methane is actually irreversibly destroyed in Titan's atmosphere, and so there should be a source somewhere, although we haven't really sorted that part out yet. It does not show up well at all. That's a very sad story. Okay, well maybe we'll just skip that slide. If you can envision for a second, maybe, those of you with very good eyesight, that there are boxes here, which show up quite well on my screen, but don't show up at all there. I've never actually had this happen before. It turns out that our UV experiments actually reproduce the observed abundances in Titan's atmosphere very well. Oh, see, look, there's a TV right there. See, look how nice that plot looks right there. Isn't that amazing? I know it's tiny and half of you can't see it, so you're just going to have to trust everyone else that this plot is amazing. This is like one of the most beautiful plots I've ever made, and it's just not. You can't even. What are you going to do? But so this is actually really, really interesting because no one has ever really demonstrated that the gas phase products in these experiments look anything like what we see on Titan. So this was kind of reassuring that we're not doing things completely wrong. And then one of the other things that we discovered is that the spark experiments produce more aromatic products and more nitriles than the UV experiments. So the data that we get from these two instruments isn't sufficiently high resolution for us to be able to identify the products really well. And so what you're seeing here is a plot of something that we call the delta index, which is just the mass of the molecule minus 14, basically. So we pull off all the CH2s and we get whatever's left. And that tells us what kind of functional groups might be there. So things that are this way are more aromatic, things like benzene, and things that are this way are more aliphatic. So we see that they tend to, the spark experiments tend to be more on the negative side of the delta index than the UV experiments, and that we also get more nitriles than the UV experiments, which is not surprising. And this is something that we would have expected from Titan. Those kinds of molecules, our benzene, our HCN, those molecules are produced in the upper atmosphere in Titan by ion chemistry, not by UV photons deeper in the atmosphere. With the spark experiments, we also have more signal at lower masses in the particles. So it's kind of interesting that we seem to be making a lot of little things with the spark experiments that aren't growing in terms of at least what's being partitioned into the particle phase. We still don't really understand why that's happening, but it's true nonetheless. And so this is just a comparison of the UV and the spark. Let's see what else. Oh, so one of the other things that we're really interested in is trying to understand kind of the absolute atomic abundances in these things, because that's something that we might be able to get a little bit of constraint on from some of the data that were taken by the Huygens Probe and from Cassini. And so one of the things that we see is that the hydrogen to carbon ratio seems to basically be constant as a function of the amount of methane that we put in the experiment, and also doesn't really vary based on the energy source. But if we're looking at the nitrogen to carbon ratio, which is shown on the bottom, you'll see that our spark experiments produce a lot more nitrogen-bearing compounds than our UV experiments. Now, I said a minute ago, at least twice, that our FUV photons cannot directly dissociate molecular nitrogen, so you may be wondering why we have any nitrogen whatsoever in the particles from the UV source. We haven't really sorted that out yet. There seems to be some kind of process involving methane, but that's still kind of an open question for us. Nonetheless, the spark experiments produce more nitrogen-containing compounds, which is not surprising, and this is also consistent with what we see on Titan. There's much more nitrogen-bearing molecules in the ionosphere than we thought prior to the arrival of Cassini, and we see that in the mass spec data. This is a comparison now of our nitrogen to carbon ratios to a lot of other experiments. So people have been doing these kinds of experiments for, depending on how you count, somewhere between 30 and 50 years. And so you might tell me that there's lots of different answers on this plot. So this is pressure on the x-axis and N to C on the y-axis. We're over here. So these were the spark experiments. These are the UV experiments. But I would say that, in fact, everybody gets the same answer. Maybe that's not quite true. But one of the things that we think that we are seeing here, at least, is there doesn't seem to be a strong pressure dependence. And this is really important because even these experiments that look like they're running at really low pressure over here at 0.1 millibar, that pressure is still pretty deep in Titan's atmosphere. So one thing that we absolutely can't do is replicate the pressure of the ionosphere in these experiments. You'll remember I said that the mean free path is 1 kilometer in the ionosphere. So you're going to need a really big chamber if you have any prayer of doing chemistry that isn't just things bouncing off the walls at that pressure. And so one of the things that is important for us to try to understand a little bit is how the fact that we can't replicate the pressure correctly is affecting our results, which it almost certainly is, unfortunately. But at least it doesn't look horrible, depending on who you ask. And one of the other things that we found by looking at the particles is that, as I just mentioned, the spark experiments produce molecules that contain a lot more nitrogen than the UV experiments. And you can really see this in this plot. So this is the percent of the total signal that's in these different kinds of groups. So we have things that have CH and N, things that are just CH, things that are just NH, things that are just CN. And you can see that for both the spark and the UV, almost everything is either a hydrocarbon or a molecule that contains carbon, hydrogen, and nitrogen. We have very little amine functionality. This has been confirmed by some other measurements that we have done. And we also have very few things that are just composed of carbon and nitrogen. Nonetheless, you can see that the spark experiments have a lot more nitrogen incorporation than the UV experiments, but I said that already. Let's see. So this is just kind of a summary of some of the things that we learned from doing this study using these two different energy sources without changing anything else. One thing that has been really nice about this is that it has confirmed a lot of what we thought we knew about the difference in energy source, but before we were comparing apples to oranges because we were comparing such different experiments. And now we've actually done it on the exact same setup, the exact same person ran the experiments. And when I did the experiments, I used the exact same gas mixture. So I ran them the same day, the UV one and then the spark afterwards. And so we really removed all of the other variables and showed that some of these things are consistent with what we thought we knew before. So the UV experiments reproduce the observed abundances of quite a few species we see in Titan's atmosphere, which is actually the first time that anybody has demonstrated this. So that was very exciting, and that was different. The spark experiments result in the incorporation of more nitrogen in the gas and the particle phase than the UV experiments, which was something that we were pretty sure was going to be true, but it was reassuring to see. The spark experiments produce more aromatic products and nitriles in the gas phase, and that also wasn't particularly surprising, but again, reassuring in terms of trying to produce an analog. And finally, both the spark and UV particles contain more nitrogen than the gas phase. So that's something that had been shown by one previous experiment, only using UV photons, that for whatever reason, the nitrogen prefers to be in the particle than in the gas phase. And so that tells us something interesting about the materials that would be available for subsequent chemistry on the surface. I'm going to skip that one. So the next question that I kind of wanted to address experimentally is, what is the density of Titan aerosol analogs? So why do we care? Well, I had mentioned that these particles that are produced in the atmosphere then subsequently do a lot of different things. So they can act as cloud condensation nuclei. They're somehow becoming the particles that form the dunes. They somehow turn into cobbles that then are transported by fluvial processes. And all of these things, if we want to study the physics, we need to know the density of the particle. So the density of the particle is an important parameter for cloud microphysics. The density of the particle is important to try to understand how things would be transported, either by wind or by liquid. But we have absolutely no prayer of figuring out the density of the actual Haze particles on Titan with any of the tools that we have right now. So we thought we could at least try to figure out the density in the lab and go from there. So this is the exact same experiment that I mentioned a second ago, but we're using one of the instruments in a slightly different way. So we can get density of the particles by leveraging these two different instruments that we have in the lab. So the AMS, the aerosol mass spectrometer, measures the vacuum aerodynamic diameter of the particles. But the scanning mobility particle sizer is measuring the mobility diameter, which is different. You might have to trust me on this. So one of them is determined by the terminal velocity of the particles, and the other one is determined by a balance between the electrical force and the drag force on particles. It turns out that a lot of lab work has been done to show that these things are related. The actual density of the particles is related to both of these with this lovely factor of rho naught in front of it, and rho naught is 1. I don't know why it's there, other than to remind us that our units are correct. Which is useful. But if we know these two things, we can get this effective density of our particles. So then the question is, what's an effective density? So the relationship between the effective density and the actual density of the particle depends on what your particle looks like. So if our particles look anything like that, so actual spheres that have little holes in them, or compact aggregates, then this effective density that we're measuring through these two techniques is actually measuring the density of the particle. Now, there's one other thing to understand, which is that the particle density is not necessarily the same as the material density. And so only a few people had ever tried to measure the density of Titan aerosol analogs before. But in all of those cases, they were measuring the density of the actual material that the particles were made out of, not the density of the particles themselves, and it's different. And the important thing about that is that for all of these models, they don't care what the material density is. They need to know what the density is of the particle itself. So this is a very powerful technique for trying to constrain this. If our particles look like this, then that's a bad day, because our effective density is less than the particle density, but by how much we don't know. So the good news is that we have done some measurements looking at our particles after we collect them, and it looks like all of our particles are spherical. So we're actually measuring the particle density, not underestimating it. So that's nice. So what does this look like? So this is SMPS data. So we're looking at diameter on the x-axis and the total amount of stuff we're making on the y-axis. And this is for a spark experiment. So the mobility diameter is shown here. So that's coming from the SMPS. And the vacuum aerodynamic diameter is shown with the dashed line. That's coming from the aerosol mass spectrometer. So the vacuum aerodynamic diameter is larger than the mobility diameter. So our density is greater than 1. And in fact, it's about 1.13 in this case. This is for 2% methane. What about the UV? So here's our vacuum aerodynamic diameter, and here's our mobility diameter. So in this case, the mobility diameter is actually bigger than the vacuum aerodynamic diameter. So our density is less than 1. And for this particular experiment, it's about 0.76. So if we look at all of our results, we find that actually, in general, the density of the particles is not that different as a function of energy source. This is really interesting because, as I just showed, we see actually quite a few differences between the chemical composition of the particles. And so whatever process is changing the chemical composition is not affecting the actual density of the particles. So the physics that's forming the particles is presumably not that different in the two experiments, which is very confusing. We don't really understand that yet. Maybe some other people in this room might have some insight. And we see that it does vary as a function of the amount of methane in the initial gas mixture. So for Titan relevant conditions, we're talking about this general vicinity. Interesting, probably the most Titan relevant one is the only one where there's a difference in energy source. So to put this in context, the value that models were using previously, the microphysics models were often using 1 for lack of anything better, honestly. And so 1 is about there. So maybe for the Titan relevant conditions, they're not doing such a bad job. But one other thing to remember is that at this point, we're still talking about, and I didn't say this earlier, our particles are spherical, and they're pretty small. The particles in Titan's atmosphere are actually fractal aggregates that are a bit larger than our particles. And so presumably our particles are more like the individual monomers in the fractal aggregate, and so the density of the actual particles on Titan might be less than what we're seeing in the lab. So that was the microphysics, but what about the models for transport on the surface? So we start thinking about what's going to float, or how are things going to get transported by rivers and streams. And the value that a lot of those models are using is 1.5. Which is significantly higher than anything that we're seeing in the lab. And that number came from some measurements of hydrocarbons that people considered to be potentially relevant for Titan materials. Now, the density of liquid methane is also shown on there, and it's actually very low at Titan-relevant temperatures. And so the important thing to see there is actually our particles would float in liquid methane, which is something that people hadn't really considered a whole lot for how you might go about transporting particles on Titan's surface. And so this is something that that might be a little bit problematic. And so people really need to rethink what's happening with these particles in Titan's atmosphere. So what have we learned about the density? Well, we measured the particle size distribution, the number density, and the particle density itself for both energy sources for a range of methane concentrations. The density peaks between 1 and 2% methane, and most of the measured particle densities are lower than the values that are used in models for all the different kinds of models, microphysics, surface transport, and some of the particles might actually float in liquid methane, which is going to change our interpretation of a lot of things that are going on the surface quite a bit. So I have just a few more minutes, so I'm going to quickly talk a little bit about the effect of CO on the formation and composition of aerosols, quickly being the operative word. So, in fact, I'm going to completely skip this slide. Other than just to say that CO is important in Titan's atmosphere, as I had mentioned, and very few people have actually looked at what happens when you put CO in one of these experiments. So I mentioned 30 to 50 years of these experiments done almost entirely using methane and nitrogen. despite the fact that CO is the fourth most abundant molecule in the atmosphere. But now we have to start thinking more broadly, right? 50 years ago, we didn't have exoplanet atmospheres to think about, but now we do. And so we need to start expanding the phase space that we're studying to try to understand haze formation, not just in the solar system, but in exoplanet atmospheres. So Karin had alluded to this before, but one of the things that we discovered when we started putting CO in our gas mixtures is that we actually make molecules that are of prebiotic interest. So we have been able to make all of the nucleotide bases that life on Earth uses. So both purine bases, adenine and guanine, and the 3 pyrimidine bases, thymine, uracil, and cytosine. We also have detected the 2 smallest biological amino acids, glycine and alanine. We see evidence for more, although we haven't been able to determine whether or not they're there for sure. We're still working on that. But this is really important because I mentioned that, if you take this stuff and you put it in liquid water, you can make these kinds of molecules. And so people have thought this way for a long time. You make the complex organics in the atmosphere, then you hydrolyze them, then you get the stuff that life might want. And what we're seeing from these experiments is that you don't need water. You can make these kinds of molecules through gas phase processes in an atmosphere. And so this might be important for places where maybe there isn't liquid water on the surface. And so, if there was life on Titan, if there is life on Titan, it wouldn't use these molecules because liquid water is not a liquid. It's problematic. So all of our chemistry is based on the fact that water is liquid. But these are a good example of the types of chemistry and the kinds of complexity that can be occurring in an atmosphere. And so that tells us that we need to be paying more attention to what kinds of things an atmosphere might produce when we're thinking about these kinds of processes. So really quickly, same experiment. This time we put CO in it. I'm going to skip all of that. So I think probably I'm going to stop after this slide because this is the most interesting thing that we found, which is that when we put CO in our gas mixture, we make way more stuff. So the x-axis is percent CO in the initial gas mixture. So no CO is over here. This is 50 parts per million, so a Titan relevant experiment. And we went all the way up to it's 5% CO in the gas mixture. And these were all for 2% methane, so Titan relevant methane. And this is a y-axis. So we're increasing the amount of stuff we're making by orders of magnitude. There's even a slight increase just for 50 parts per million CO. So this is for the UV. I don't want that one. Well, actually, here, this is SMPS. So just to show you the difference between 2% methane and 2% methane with 5% CO. So we make way bigger particles. We make more of them. If we do the UV source, we do the spark source, we see the same thing. So in both the spark and UV, as we put more and more CO into the gas mixture, we get more and more stuff. I wanted to see if I could try to get this curve to turn over, but for experimental reasons, I couldn't put more than 5% CO in our experiment. So I don't know what happens if you keep going. Someday I'll answer that question. And then one of the other things we can address is what is causing this trend. And so we see actually 2 things. So we're increasing our particle size. When we put CO in the gas mixture, we make bigger particles. So this is important for trying to understand radiative processes in the atmosphere. But we also make more of them. So this is number density as a function of percent CO. So we make both larger particles and we make more particles. And so something about the CO is increasing how effective nucleation of particles is in these experiments, but it's also increasing the efficiency of growth in the experiment. And then this is the last thought, I promise. This is not simply a result of putting more carbon in the system. So everybody always says to me, well, Sarah, you put a whole bunch of CO in the system. CO contains carbon. Carbon likes to make chains, and so that's what you've done. Congratulations. But we know it's not simply a result of putting more carbon in the gas mixture. So this is just looking at methane now, without any CO. So as we increase the methane mixing ratio in the experiments, for the spark, our loading actually goes up for a little while, but then it turns back over. So as we put more methane in the experiment, we make less stuff. And for the UV experiments, the more methane we put in the experiment, the less stuff we make. And so it's not simply a result of putting more carbon in the system. There's something different about having the CO available. And in fact, okay, I lied. There's one more. Not that one. This one. Okay. This is really the last one, I promise. We can see that it's not just the carbon, because if we do aerosol mass spec on these experiments, which is what these data are from, so this is percent CO in the gas mixture. This is 0.1% methane this time. This is weight percent of the different atoms. And so what we see is that as we increase the amount of CO in the experiment, we see more oxygen in the aerosol. So it's not like we're just producing aerosol that is carbon rich, but we've put more carbon in the system. We're actually incorporating this oxygen into the aerosol, and that's certainly playing a role in this chemistry. And so that's kind of one of the points that we're at right now, is trying to understand why the CO is doing this and what other molecules we've overlooked that might be very important for haze formation. So kind of the takeaway message of this section is that we have had this very specific idea of haze formation in planetary atmospheres, that you have methane. Methane has this carbon. We make these long organic chains. That's how you get haze. If you don't have methane, you're not going to make haze. And what I would like to try to start to show you is that there are many different ways to make haze in an atmosphere. And so as we start to see these very different atmospheres across the universe, we need to be a little bit more open-minded about how you might go about making an organic haze. If you're not just talking about a methane mixture. I don't know what the next slide says. This is just a summary of the things I just said. So the particle size, number density, total mass loading all increase as a function of increasing CO for both the spark and UV. I'm not that one I don't care about. We'll skip the second one. And then the end, the aerosols become more oxygen rich as we increase the abundance of CO in the experiment for both the spark and UV. And so there's some kind of interesting process that's occurring. And with that, I would love to take questions.
Thank you for that really interesting and laboratory-based talk. And yes, open for questions. I see. Please.
Could you talk a little bit more about the implications for exoplanet atmospheres?
So the question was, what about exoplanets, Sarah? Is that a good paraphrase?
Yeah.
Right now I don't know. So,
or possibilities.
Well, yeah. So there's a couple of different ways to approach starting to move into exoplanet phase space. So the experiments with CO were done with an eye towards exoplanets, but they were done at room temperature. And so, I forgot a slide. Can I go one more? No, okay. This is as promised. I have a lab at Hopkins. It does things. We have no data yet. We just turned this on last week. But look, it goes. We can do science soon. So there was a point to that. But thank you for reminding me. My approach to trying to get into exoplanets is to, hold on tightly to the 50 years of work that we've already done. And so rather than just increasing the temperature in the chamber by 500 Kelvin and seeing what happens, we're going to try to move into that phase space from the solar system experiments that we've already done. And so the CO experiments were kind of a first step of expanding our composition space, but this experiment that we built at Hopkins is much more flexible than any of the experiments that currently exist. And so we're going to be able to do a much broader range of temperatures, we're going to be able to do a much broader range of pressures. Composition is actually the easiest phase space to explore for the most part. And then right now we're using a plasma, as you can see, but we also will be able to use UV source, and so we can look at the different options for energy. And so in terms of exoplanets, I think the answer right now is really I don't know. But I think, at least from the CO, we're learning that, again, there are different ways to make an organic haze, and people have really discounted the role of oxygen and oxygen-bearing molecules for haze formation, because a lot of experiments that were done with CO2 showed that putting oxidized molecule into the experiment pretty much just destroys haze formation. It's true for CO2, it's true for O2. But if you put carbon monoxide in the experiment, you get very different results. And so I think that that's at least something that we've really learned that I think will be important for exoplanets. But until I run this experiment at a higher temperature for you, I can't promise that it's still true.
I think Gary was first. And then
as I understand it, the challenge is to build up such large molecular structures in an environment that has such a long mean-free path. Is it possible that the process is working in the other direction, that what you're seeing is the breakup of larger things like PAH dust particles?
Yeah, so that was, I think that was pretty much everybody's first inclination when we started seeing this, is okay, there's dust coming in, that's what we're seeing. And it turns out that both sides use the exact same argument against each other. So the fact that the mean-free path is so large means that this is not the region of the atmosphere where the dust particles stop. right? They haven't run into enough things to lose the energy that they had. And so dust actually gets deposited much deeper in Titan's atmosphere. And so we have a mean-free path problem on for either explanation. And this is something that we can only answer if we can measure the composition of the particles. So if you would like to tell NASA, like I plan on telling them over and over, hopefully not for the entire rest of my career, that we need to go back and send a very high-resolution mass spectrometer to answer this question once and for all, we're not going to really be able to get much more information to answer that question.
JWST won't know?
No, we can't. I don't even know if they're going to be able to do... Oh, no, they will be able to do Titan. They have a Titan working group. We can't do remote sensing very well of the upper atmosphere. The densities are so low. If you want to measure the composition up there, you have to send a mass spec. It's pretty much the only way. So, if you want to tell NASA that too. But we are, and so one thing I didn't mention, I had thought about putting in this talk and I didn't, but one of the other reasons that we go through all of these shenanigans of trying to make these particles is, we're never going to perfectly reproduce the atmosphere in the lab. That's not the point of these experiments. But one of the things that we can use these experiments for is to start testing instruments. And so one of the things that I've been working on a lot lately is development of the highest resolution flight mass spectrometer. So we're working on an instrument called Orbitrap, which is the highest resolution mass spec that you can have in the lab on Earth. And we're working on miniaturizing everything so that when NASA decides that it's ready to go back to Titan, that we will have the highest resolution instrument that you could have in an Earth laboratory, but ready to put on a spacecraft. And one of the ways that we're doing that, one of the ways that we're able to do that is by using these analogs that we produce in the lab to test the instrument on Earth so that we don't end up with valves that are clogged or the wrong resolution or all of these other things. And so that is something that that is another reason why we do these types of experiments in the first place.
Thanks, sir.
I was wondering, I know you didn't have the time to go into early Earth implications. But
I have a whole bunch of slides.
Yeah, no, I'm really curious, especially with the Haze formation, and you're kind of hinting with CO, and previously people only looked at CO2 and CH4 ratios. So could you maybe talk about what you're finding that is it with the addition of CO that's causing maybe some implications for early Earth?
So the early Earth section was this fun thing that we did where we put oxygen in our experiments, O2. Which I can tell you, when you are putting methane and O2 in an experiment with a Tesla coil, you quadruple check your numbers that you've calculated, and then you do the experiment on a weekend when nobody's in the lab, because, it's one thing if I take myself down for my science, but it's another thing if I take everyone else down with me. But we didn't blow up the lab, it's still there. So one of the things that we found, which is quite interesting, is that the addition of small amounts of O2 actually increases haze production. And so we weren't interested in the regime that most people have looked at for early Earth experiments, where they're just using CO2 and methane. But I actually wanted to know is, a lot of ideas about the early Earth kind of treat O2 as a light switch, essentially, that the second there's O2 in the atmosphere, the haze layer is gone. And so I want to know, is that really true? Is there going to be a period of time where the haze is thinner? That has implications for the radiation budget. It turns out that a lot of the results from this experiment are showing that the composition of the particles changes quite a bit, and in ways that might be interesting and relevant for any kind of early life forms. And so I think the haze story for the early Earth is probably significantly more complicated than we thought it was. And one of these days I will finish analyzing this data and write that paper.
Mark.
So you mentioned Titan as being the only other place we said the Earth was substantial nitrogen atmosphere. Less substantial, true, but Triton and Pluto also have atmospheres that behave like atmospheres that are nitrogen. They have CO. I'm just wondering, this is sort of like going the other way. Instead of adding temperature, or subtracting a little temperature and reducing the UV field, which you would expect haze production to proceed similarly, and can we learn something particularly from New Horizons that might add a little more to this?
Yeah, I mean, I'm sure you know this, but maybe everybody else doesn't know this, that there's been kind of a long-standing debate about whether or not Pluto has a haze layer. I can't imagine Pluto not having haze, at least at some points in its orbit, based on the stuff that we've been doing. When you have methane and you have CO together, I can't not make haze in the lab, no matter how little methane I get it or how little or much CO I give it. If there's energy in those two molecules, I make particles. And so I would be very surprised if Pluto does not have haze in its atmosphere, at least at some points. And so I'm super excited for the results from New Horizons, because then we'll have another data point to start trying to test our ideas about how haze forms in planetary atmospheres.
It's probably a naive question, but can you draw a parallel to the forest fires in Earth's atmosphere, which is basically an enhancement of CO? So, and that's actually one of the major productions of all kinds of nasty cases. So
this is one of the things that I learned. So I was an NSF Astronomy and Astrophysics postdoc in the Cooperative Institute for Research in Environmental Sciences, which is the weirdest combination of two things I think you could come up with. But I learned a lot from the Earth community, go figure. And I think one of the most important things I learned is that we've actually been very naive about the behavior of oxygen and particle formation this whole time. The early experiments that were done using CO2 and methane, I think, really did us a disservice, because when you have oxygen, and this is what you're referring to, so when you oxidize a lot of gas phase volatile molecules in Earth's atmosphere, your products are actually much less volatile, and so they will partition into the solid. And so on Earth, when you oxidize these products from forest fires, biomass burning, these kinds of things, you make more aerosol. And so I suspect that's exactly what's happening in this experiment, that these oxidized products are less volatile than what we started with. There's also an issue where we have shown, and prior work has shown, that the more H2 you have in the experiment, the less product you make. So it's possible the other thing that's happening is that some of this oxygen is actually pulling H2 out of the system, and that's also enhancing the particle formation. But of course that can't be the only thing that's happening, because as I showed, there is oxygen in the particle phase as well. So it's not simply a gas phase process that's enhancing this production. Something is also happening in terms of the solid particles. But you're absolutely right, and that's something I think that my experience hanging out with the Earth people has really helped me with quite a bit.
So I have a question about temperature.
No!
So in Titan's upper atmosphere, it's high energy photons which are causing the ionization.
Mm-hmm.
And if you're using sparks, you get that ionization. Presumably you should have peak temperatures in the discharge which are high as well. So do you worry about the thermochemistry? How do you think that should positively affect any of the results?
We worry about all kinds of things. Yeah, so the electron temperature in these plasmas is obviously quite high. The neutral temperature is actually not too bad for the most part. It's still not Titan-like, but it doesn't get that much hotter than what we started with. So in that sense, that's at least somewhat reassuring. But it's just, I mean, I hate to I feel like such an experimentalist when I say this, but it's really hard to make an experiment that's correct. And so, we do the best we can with the energy source and the temperature and all these other things. But at some point, there are so many factors that are difficult to measure in the experiment, like the electron temperature and the neutral temperature. But that is something that we're hoping to do a better job of with the experiment at Hopkins, is characterizing the energy environment in our plasma. Because people have not really focused much on doing that. And I think that's something going forward that we really need to do a better job of. Because what I would really like to do, having come from modeling a long time ago, it feels like at this point, is to actually start trying to use our models on the experiments, right? That seems like a natural thing to do. That hasn't been done as much as you might think. But part of the reason for that is that we really need to know a lot more about the energy environment before we can start trying to use the models to see what's happening in the experiment. So we don't know as much as we would like to know about that, but it does keep me up at night.
So I think last question down there before you head up.
Okay, it seems like one of the biggest problems is the density issue of the molecules. At the levels where they're going to get the energy that will do the work, is there any are there people looking at dynamical models that could create concentrations? Like if an eruption from Enceladus hits all at once or something like that, that could cause enough density to have reactions?
People have thought about possible dynamical explanations for that, and nobody's come up with anything that's even remotely plausible. Which doesn't mean that that's not what's happening. It just might mean that we need to be more creative. I suspect that the explanation is still chemical. There's there's things that happen with ions that can kind of end up in some of these runaway processes where you could envision building very large things. You just have to do it very slowly, I guess, since your collisions are not happening very often. So I really think the explanation is chemical, but it's still something that people are trying to understand, if maybe there is either a simply dynamical explanation or if there's some kind of coupling between the chemistry and dynamics that's resulting in this kind of process.
So before thanking Sarah again, I just want to say that for those that I caught up now and have more questions, that Sarah will be around tomorrow, so please email me or Sarah directly if you want to chat with her. But with that, thank you so much.